Well, thank you. Thank you for coming today. Energy Basics is a great title for my presentation today because we're talking about some of the most basic thing in a building. I'm pretty much sure that every last one of you has an air duct somewhere in your home or in the property that you work with. And we're going to be talking about those air ducts today. We know that the problem of air duct leakage is pervasive. In fact, in the last 10 years, we have learned so much about this problem that we didn't know. If you talk to a building commissioning engineer, they'll tell you that 3/4 of the time when they go into a building, they try and commission that building. They're trying to get it to balance. It won't balance because the air ducts leak too much. If you read the ASHRAE handbook on duct design, it will tell you that 3/4 of the commercial properties in the United States, 3/4, have gross duct leakage, anywhere between 10 to 25%, way beyond the number that was designed by any engineer in any sort of calculation. Not only is it a pervasive problem in the sense that it's everywhere, it's an absolute consequential problem. It generates a tremendous amount of energy waste. A recent study by McKinsey Consulting said it's the single biggest factor. A recent study by Lawrence Berkeley National Laboratories on recommissioning buildings said the #1 energy savings opportunities in properties in the United States is to get rid of duct leakage. In fact, they ranked it higher than occupancy settings, turning the lights off when you leave the building, things that we would think of immediately when we think about energy savings. In fact, according to the EPA, $25 billion a year is wasted in energy in this country alone just with duct leakage. So it's a huge problem and it's pervasive. Talk a little bit about what goes wrong in a building if the ducts are not properly sealed. When you have air duct leakage in a building, air leaks out of the air ducts and it does not get into the occupied space. What happens is it gets sucked back into the return or into the exhaust stream. And so it's short cycling. So your air conditioning system is running and running and running, trying to satisfy the temperature in the space, but it's not able to do that because it's losing so much air above the ceiling. It's wasting money. All of that excessive runtime causes 3 bad things to happen in a building. The first thing is those fans run longer. Okay? We know from ASHRAE that 20 to 60% of the HVAC operating cost in most commercial buildings is to run the fan. 20 to 60%. So if you're short cycling your HVAC system and causing the fan to run longer than it should, you're going to rack up a huge expense. And the question is, why is that happening? It goes back to the fundamentals of engineering design. We know that whenever you want to double the flow of a fan, what do? You speed the fan up, right? The speed of the fan and the flow of the fan are proportional. We also remember that the speed of the fan and the power required to turn that fan go with the power of the cube. Think about that. If you're going to double the speed of the fan, the power increases to the cube. So what does that mean as a design engineer, as a facility engineer? You increase the fan in your air handling units to overcome even a 20% duct leakage, you're going to increase the power required for that HVAC system to go up over 75%. That's the penalty you pay every day if your duct systems leak even a little bit. It's a huge amount of energy waste. The second thing that happens in an HVAC system when you have duct leakage, and this is not quite as obvious, but think about this for a second because it's common sense. Where are the drives? Where are the motors in a typical air handling system? They're inside the box, right? And so as the fans run, what happens is you start to generate X heat. And that heat becomes a cooling load during your cooling season. In fact, think about it. For every kilowatt of energy generated by your fan, you're going to generate 0.3 of a kilowatt of heat. So the second way you pay whenever your ducts leak in a commercial property is not only does it cost you more to run the fan, but now you're generating a heat load for the building that you don't need to have. And then the final problem that you've created in a commercial property whenever you have duct leakage is you're bringing in ventilation air. As you can see from the graphic, we're pulling in outside air. We need fresh air in the building to make sure that good indoor air quality. But the problem is if your fan is running more than you need, you're bringing in ventilation. Think about it like this. If you pop your ceiling tile, do you need fresh air in your ceiling vents? Do you need fresh air in your vents? Well, if you have air duct leakage, that's what you're doing. You're paying for your air conditioner system to condition air, and you're running it through interstitial spaces. It's a waste of money. So those are the three first-order bad effects that we can think of in a commercial property. So that's why engineers and scientists tell us you need to make sure that your air distribution system is as tight and as efficient as the HVAC system it's connecting up to. So how do we deal with this threefold effect of wasted energy from fans, wasted energy from the HVAC system heat, and wasted energy from the outside air? Well, traditionally, there hasn't been a whole lot we can do. We know that if you've got installed air ducts in the building, they're very difficult to get to. They're very costly to tear out. Very labor intensive to pull down all of the ceilings and all of the walls. So traditionally what happened is people ignored the problem. For years and years and years, we've known the consequences of air duct leakage, but we didn't have any really good way to deal with it. What did we do? We typically turned up the speed of the fan. We just ate it from an energy perspective in order to get the ventilation in the proper that we thought we needed. That wasn't a good solution. It's not a good solution for the environment. It's not a good solution for us as individual consumers and properties. And so enter your U.S. government at Lawrence Berkeley National Laboratory. 20 years ago, they took on this challenge. They said, there's got to be a better way. There's got to be a way where we can take existing properties and we can fix this #1 energy waster, but do it in a way that's not disruptive and it's not cost prohibitive. And they had these goals when they set out. They said, we want to find something that gets to all of the duct system, not just the parts that we can see. We want to do it in such a way you don't have to tear down the walls. We want to do it in a way that's cost effective for the end user. We want to make sure it's safe, and most importantly, we want to make sure that it's effective. And after many years of research, 20 years ago, they developed aerosol duct sealing at Lawrence Berkeley National Laboratory. And the idea was that they were going to use aerosol as a way to seal up ductwork and avoid all of the negatives that we had traditionally associated with duct sealing. I'm just going to take a minute and explain to you how aerosol duct sealing works. The vision was the contractor would come into the building without pulling down the ceiling tiles. They would simply go to all of the vents and block the vents. Then they would block the air handler. Now there was nowhere for the air to go but through the holes. Then they would connect a fan to the duct system, and that would push air through the holes. Then they would create an aerosol. In the Lawrence Berkeley National Laboratories, they envisioned this aerosol to be something safe and benign. In fact, they used a product, a vinyl acetate product, that was a base for chewing gum and babies' pacifiers and latex paints and hairsprays, something that was very benign but inherently very elastic. Turned it into an aerosol and pushed it through the duct system. It traveled at about a pace of a slow walk, relatively low pressure, low flow. But when it went to squirt through the holes, it got very turbulent as it pushed through the holes, and the sealing particles would build up around those holes and form a plug. And the idea was that in this way they could seal up all of the holes in the ductwork without actually touching the inside of the ducts. Their vision was, well, let's take this great system, let's put a computer on it. And if we put a computer on it, we can do some very cool things. The first thing we can do is we can control the process. So rather than trying to paint the ductwork and pray that it works, now the technician or the contractor is in control of the results. They can watch the ductwork getting tighter, and when it actually is tight enough, they can stop the process. They can test in and they can test out. And they can also start generating some reports and tracking and preparing and presenting measurement and validation programs. And so this was their vision of how it works. And you can see from the graphic on the top right-hand corner, it was a very simple process. There was a fan that would push the air through the ductwork. There was an injector that would create the aerosol. And that was all there is, just two moving parts. And you add a computer to that, and voila, now you've got a system that can fix ductwork. Down on the bottom, you can see some pictures. On the right-hand side there, you can see a picture of what the sealant actually looked like when it goes into a hole. It just looks like a little white plug. In the center graphic, you can see what the machine actually looks like today. So here's some graphics and some pictures so you can see how this aerosol technology is applied in a building. There is a good picture of a contractor. You can see it's working at technician, and you can see in the background the tube where the machine is connected to the ductwork. So that's where the aerosol is going to go into the ductwork. There's an example of the contractor creating the point where the aerosol is going to go into the ductwork. There they are again, connecting the tube to the ductwork. And here they are connecting the machine to the ductwork. And there's the computer that controls the whole process. Now I want to give you a specific, I'm going to take a few minutes and talk about a very specific application of how you can use this technology to save money in a building. This is in Washington State. It's the Skagit County Administration Building. And if you look at the property on the left, it kind of looks funky, doesn't it? Kind of round shape, not very many windows, kind of architecturally significant. Well, like a lot of us, they want to save energy. In fact, they had a performance contract out for bid. But like a lot of us, we're faced with every day, it wasn't just about saving energy, right? It was about, in this case, creature comfort. This building was awful to live in. It was cold in the winter and hot and stuffy in the summer. And so when the client approached the contractor and said, hey, we want to do this. We want to save money on our building. But you know what their number one priority was? We need to feel good about our building when we're done. It needs to live better. It needs to have better air quality in it. So now you've got a challenge. What do? You at one hand, you want to save money. On the other hand, you want to deliver more conditioned air to the space. So the contractor visions that this is a perfect application for aerosol duct sealing. Because the ceilings, it's very difficult to access the ductwork. I think this is a situation where we can go back and we can remediate the ducts and we can see them. So the client had all sorts of expectations. It was an operating courthouse. They didn't want to have disruptions. They wanted to be more comfortable. They wanted to save money. Does it sound kind of familiar where they're just kind of stacking all sorts of requirements on top of it? And so they came in and they did the aerosol. And you can see the first thing that they did is they took the air handling systems. There was 4 air handling systems. They blocked them off. They sealed the ductwork. They went to the next one and the next. And within 4 days, they had sealed up all of the air ducts in the system. In fact, you can see they went from losing on average 40 tons of cooling every day down to losing 4 tons of cooling. 40 tons to 4 in just 4 days. That was over a 90% reduction in loss. That saved them over $3,500 a year after they had added more air to the building to improve the indoor air quality and the comfort. In fact, when the contractor went through the process, they figured out this entire exercise paid for itself in less than 4 years. Here's another example. This is a school district in central Ohio. Anybody from Ohio? Yeah, so this is right in smack dab in the middle of Ohio. Lincoln Heights, small school district. This is a K through 3 school, and there was a 4 through 8 school down the street. This one was called East, and guess what? In Ohio, we're very creative, and so what do we call the one that was down the street? We called that one West, right? The problem with this school district, with this particular school, is it was identical footprint, identical location, 30% higher energy consumption than its sister school. In fact, they had 2 40 horsepower fan motors that ran 24/7, 365, no setbacks. And so the school districts asked the obvious question, why is the energy consumption in this school so much higher than its sister school? They called it engineer in. The engineer did an application. You know what they found? They found that air ducts were leaking. So they had a contractor come in and use the aerosol duct to seal up the ducts because they had a very limited period of time, just 2 weeks. The school was brand new. It was less than 7 years old. The last thing they wanted to do was start tearing down ceilings and walls and so on and so forth. So they were able to schedule this over a winter break. They were able to seal up the ductwork without disrupting any of the staff that was in there during the winter break, and then they were able to get a great amount of success. In fact, you can see how much money they were saving per year. It got to the point where the utility actually generated a rebate of over $27,000 and gave it back to the school after the job was done, just in appreciation for the amount of energy that they had managed to save on this one project alone. Here's another quick case study in New York City. You can see, again, same type of idea of savings. And the last project I wanted to talk about is a hospital in central New York. Over 100-year-old building, very diverse application, very similar. Because of the age of the building and the way it was constructed on over years upon years upon years of addition, there really had been no major renovation. So as a performance contract, contractor went in and they created a bunch of remediation in the building. In this particular application, they realized that the air ducts just were not sealed properly. So they were able to go into an existing operating hospital without disrupting doctors, nurses, and patients, be able to seal off all of the vents, install the aerosol duct sealant, and you can see the reduction in leakage was dramatic. Over 97% of the wasted air was removed and now is correctly applied. And they were able to save almost $28,000 a year annually. Payback for this job was probably in the neighborhood of 4 to 5 years. So that's what I've got. That's a basic energy technology. So any questions? Yes, sir.
VAV boxes, you're sealing the duct. Can you sell them the VAV boxes with reheat coils in place?
So that's a great question. We're talking about VAV boxes because you've got, in a VAV box, you've got a coil and we've got a measuring device, typically a flow ring, right? So the way we would do this is the contractor would block off that VAV box so the sealing material would go up to but not through the VAV box. That's the way it would work.
Downstream of it.
Then they can either bypass that and go downstream, or in some cases, if there's not a whole lot of ductwork, they might just manually seal the ductwork downstream from that. But that is an important consideration. Good question. Yes, sir.
Sorry. Just for your K-3 example and this example, what was the total time from start to finish?
A week and a half. They had Christmas break to do it. The principal was insistent because she was at the end of the run, and unfortunately the kindergarten class was next to her. And every winter, right about Christmas break, the kids would go home and tell mom that they had to wear their hats and gloves all day in class. And she was insistent that she wasn't going to have another winter of that. So just about 2 weeks. Yes, sir.
When I bring up a set of energy conservation measures to a client, I like to be as predictable as possible, costs, savings. Is this process conducive to a diagnostic round that would tell me roughly how much energy I'm losing so that I can then talk about costs for remediation? Or does this sort of have to be done all as one thing? Is that generally the way it has to be implemented, all as one step?
That's a great question. But how do you approach your client?
Right.
And how do you set this up?
Because I'm not wild about asking them to bring a contractor out to test for leakage that's going to cost them X thousand dollars, only to find there's very little, and that has a negative payback.
Absolutely. So the best way to approach this with your client is to start off with a consult with the manufacturer. They will give you an initial payback. They'll kind of give you bigger than a bread box type of stuff. Then you can take that to your client, and then whenever they go through, for example, an IGA phase, then at that point in time, you can bring the contractor in and they can walk the building, they can validate the assumptions, they can sharpen their pencil, and they can come up with a firm payback. But I usually like to start off with just a general discussion or even a set of prints and some 7 basic questions, and from that we can usually get a pretty good payback.
What are the questions you ask to try to diagnose whether or not this problem exists?
Well, we know that the problem almost always exists. We have a scorecard that we use, and if you come visit us, I'll give you a copy of the scorecard, and it's something that somebody can use as a self-diagnostic, or you can use as a way to have them pre-educate themselves about whether or not they've got the problem. Okay? Yeah. Yes, sir.
What size hole is too big for this to work?
Great. So the question is, how big of a hole will this fix? It'll do a seam that's come apart that's 5/8 of an inch wide or about the size of a quarter. So it's pretty big. Yes, ma'am.
How are you calculating your leak rate?
How am I calculating my leak rate? So there's the way we're doing it is kind of the industry standard practice. We do a static pressure test, which is we have a digital manometer. So what it's doing is it's reading the static pressure in the ductwork. It's ramping up the variable speed fan to maintain the pressure in the ductwork, and then it's using the other lead from the manometer to read the amount of flow that's going into the duct. So flow in equals flow out. Does that make sense? Okay. Yes, sir.
In terms of toxicity, what are you talking to people about? I mean, putting it in a hospital or schools.
Mm-hmm.
What is the material?
So great question. What is this stuff you're spraying in my ducts? Probably the number one question. Vinyl acetate polymer, a base for chewing gum. MSDS sheets, product data sheets. We find is that 95% of the time, the folks in the hospital or the school district are happy. If you're anybody from the state of California, meets all of the state of California. California has some of the toughest toxicity rules in the nation, meets all of their requirements. For example, LA Unified School District does this extensively under Title 24. Every time they replace an air conditioner, they have to fix the ducts. Yes? Yes, sir.
Is there a way of measuring the temperature in the plenum chamber to see whether when it's running, the temperature changes because of these leaks?
So good question. Is there a way of measuring the leaving air temperature from the air handler?
No, in the plenum.
In the plenum section? That's a good question. I'll have to think about that. Can I think about that and get back to you? All right. That's a good question. Yes, sir.
Is there a life cycle of this stuff?
Good question. How long does it last? It lasts for 40 years, according to the Department of Energy. Yeah.
There's no flammability kind of.
No, no. Yes, sir.
Increase in duct-free systems after this application?
Great question. What does this do to my static pressure drop in my ducts? Well, since it doesn't coat the ductwork, it only sticks in the holes, there's no difference in pressure drop in your ductwork. Good question. Yes, sir.
Does it work both with rigid and flex duct systems?
Good. Yeah, what does it work on? This stuff sticks on everything. It's chewing gum. I tell people all the time, if chewing gum sticks to it, this sticks to it. So it works flexible, it works line. It even works on some non-traditional materials we'll see in venting, like masonry block versus drywall material. So it really does stick to anything. Good question. Yes, sir.
Is it applicable to clean rooms?
Good question. Yes. Can we do this in a clean room environment? Absolutely. It's been done, lots of case studies out there of this type of stuff being done in a clean room environment. So that's a great question. What other questions? Yes, ma'am.
So if it's only sticking to your holes,
Mhm.
what is causing it to become suspended from the aerosol that you're shooting?
Great. You're bringing up my worst fear. So as mechanical engineering, I absolutely hated fluid flow. I was all about dynamics. I was going to design race cars and all of that, and I am stuck with this. And this has everything to do with the Reynolds number. So we remember, if you're an engineer, you remember that horrible class when you took as a sophomore engineer, fluid mechanics, right? The Reynolds number. So we have laminar flow and we have turbular flow. And somewhere in the middle, we have something what's called semi-turbulent flow. And we know that whenever you take any sort of liquid or gas and we run it down a pipe, there's always what's called a boundary layer. And anybody kind of roll back to sophomore year in college? And so what happens is that whenever you have very turbulent flow down a pipe, the boundary layer is very, very thin. But whenever you have very slow-moving laminar flow, the boundary layer is very thick. All of this computer technology does is it creates what's called semi-turbulent flow. We control the flow of the air and the pressure of the airstream so that the Reynolds number stays below 100,000. And so that's why there's always a boundary layer, so it doesn't stick to the duct walls. But whenever we get to the hole, the hydraulic diameter, we're talking about Bernoulli's equation again, is small enough that the Reynolds number goes way up, the particles become turbulent, and they stick. So unfortunately, this is a great example of basic fluid flow dynamics. Yes, sir. Yes, sir.
How does that affect the heat sensors, temperature sensors, smoke?
Great question. What am I going to do with my smokes, my pressure sensors? So what the contractor does is they temporarily remove all of that stuff and they put it all back in when they're done. Typically, the material doesn't stick to it, but it's a good precaution. Yes, sir.
How long does the repair last?
The repair lasts 40 years. Yeah. Yes, ma'am.
Is it something that any contractor can do or maybe your company does?
So any contractor that has the equipment can do the fix. Yes, yes.
Is that equipment and training or just equipment?
The technology is licensed by the Department of Energy, so any contractor that has the equipment has been trained by the manufacturer on how to correctly install it. Some people might just do homes, others might do commercial buildings. Thank you, Asad. Yes, sir. Any questions? Any more questions? Yes, sir.
Is it worth looking at duct design for loss versus duct leaks? I mean, are you still going to get high ROI on a poor design?
Yeah, Charles, that's a great question because when we think about energy basics, which is what we're talking about today, the energy that we transfer through the duct system is really two things, right? We think in terms of the physical leaking of the air out the ductwork, and then we think about pressure drop because of poorly designed ductwork. My personal experience for doing this for many, many years is about 90% of the time, it's not pressure drop, it's actual physical duct leakage. But you do have to be aware that you want to have ducts that are designed in a way where they don't have a lot of pressure drop. And flexible air ducts can be some of the worst, right? We've seen them, they sag, maybe there's 5 feet of ductwork laying on the floor when there doesn't need to be. And so those are sorts of things that whenever you bring in an aerosol-based contractor, they should be looking at the whole thing. They shouldn't just be connecting the tulip, but they should be looking at the entire air distribution system and making those types of recommendations, so when they see pressure drop problems, then they get fixed. It's a good question. Other questions? Well, thank you very much. I appreciate the time today.